Today, we are going to be talking about the very important molecule, fructose 2,6-biphosphate, and its role in regulating glycolysis and gluconeogenesis. To start off, let's talk about the step that fructose 2,6-biphosphate participates in for both glycolysis and gluconeogenesis. In glycolysis, we have F6P converted into F16BP, and we have the reverse for gluconeogenesis. In glycolysis, F6P is converted to F16BP by means of phosphofructokinase 1. This enzyme phosphorylates the F6P by adding a phosphate to the carbon 1. In gluconeogenesis, F16BP is converted to F6P by means of the F16BPase. F26BP regulates which reaction will occur by either its absence or presence. But let's take a step back for a second. As you may remember, there are two very important hormones that help regulate glycolysis and gluconeogenesis: insulin and glucagon. Glucagon helps to reduce the amount of F26BP present, while insulin increases the amount of F26BP. What does this mean? How does this occur? What exactly does F26BP do? First, let's talk about F26BP. F26BP acts as an inhibitor of fructose 1,6-biphosphatase. So, when F26BP is low, fructose 1,6-biphosphatase becomes more active. This leads to more F16BP being converted into F6P, guiding the reaction towards gluconeogenesis. However, when there is a higher amount of F26BP present, this reaction is inhibited, and the reactions for glycolysis are stimulated. Now we are presented the question, what determines the levels of F26BP present? The answer to this is simple. But in order to explain this very simple answer, we need to discuss a very important enzyme. Well, it's not that simple of an enzyme. In fact, it is a combined enzyme, PFKFB. PFKFB has two parts: phosphofructose kinase 2 and fructose 2,6-biphosphatase. When this enzyme is phosphorylated, fructose 2,6-biphosphatase is activated while PFK2 is inhibited. When this enzyme is dephosphorylated, fructose 2,6-biphosphatase is inhibited and phosphofructokinase 2 is activated. Now, if you have not already observed, when this combined enzyme is phosphorylated and F26-biphosphatase is activated, there will be a decreased amount of F26BP, therefore causing a lack of inhibition of F16-biphosphatase, therefore converting F16BP to F6P, therefore leading the reaction towards gluconeogenesis. Now, conversely, we can see that when the combined enzyme PFKFB is dephosphorylated, PFK2 is activated. This leads to an increase in F26BP, which stimulates PFK1, therefore stimulating the conversion of F6P into F16BP, therefore leading the reaction towards glycolysis. Make sense? Perfect. Now, back to our easy question. What determines the levels of F26BP present? What's our answer? Correcto. The levels of F26BP is dependent on the phosphorylation or dephosphorylation of our combined enzyme PFKFB. One last question. What phosphorylates and dephosphorylates PFKFB? As you may remember, we have two hormones that help regulate glycolysis and gluconeogenesis. Remember them? They are insulin and glucagon. When insulin stimulates the cell, our combined enzyme is dephosphorylated, therefore leading towards glycolysis. And finally, when glucagon stimulates the cell, our combined enzyme is phosphorylated, therefore leading towards gluconeogenesis.